Hi guys, and welcome to part 2 of gas exchange, which is chapter 18. So we're thinking about partial pressures of gases now in a liquid. And it depends on how much of the gas is dissolved in the liquid, right? That partial pressure is going to depend on, did it dissolve or did it not dissolve in that particular liquid that you're thinking about. But how does it dissolve? So we're thinking of oxygen, we're thinking of carbon dioxide. How is it dissolved in the blood? Well, if a gas is under any sort of pressure and it's placed in contact then with water, it will move into that water. So with the can of soda here as an example, that's done under high pressure. So they get the cans and they put them under very high pressure and they blast that CO2 in and then seal it. So that's how they make a lot of it dissolve. They also use it chilled, which makes it be even more soluble in that liquid. And then they measure it in pounds per square inch. So it's interesting that some cans of soda have way more bubblies, right? Higher PSI than others do. And I looked this up, and it turns out that Pepsi has one of the highest carbonations of sodas. It has 40 psi. And then it's interesting to look at something like champagne. And champagne is a lot of bubblies in there. So there they do it under very high pressure and then, seal it with, obviously, with a special cork. So that's how it's done in a can of soda, but we're not thinking of that. We're thinking of the body. We're thinking, how do we dissolve that carbon dioxide and how is that O2 dissolved? So let's go to that. We have to think about what factors are going to affect the movement of that gas into that liquid, right? The movement of that carbon dioxide into the blood, the movement of that O2 in order to transport it. Well, it's going to depend on these things. First, it's going to depend on the solubility of that particular gas. So how do you know what the solubility of oxygen is or of carbon dioxide? That's something you'd have to look up in the chem manual and find out what the solubility of that particular gas is. 2, it's going to depend on temperature. And you know this because if you leave a can of soda that has dissolved carbon dioxide in it out on the countertop, it's going to lose that carbonation more quickly than if you leave it in the refrigerator, right? So lower temperature will hold on to that CO2 for longer. And 3, the pressure gradient of the gas. So how much of that gas is present to be able to become soluble in that fluid that you're presenting it to. So these diagrams are very helpful. The first item that I said to you is the solubility of the gas, right? So let's go to that. The number of gas molecules that can dissolve in the liquid is what's going to define the solubility of that gas. So look on the left here. This initial state, we have a fluid, let's say it's water here, and we have a number of particles here, which are of a particular gas. Here it's oxygen. And that pressure here in this container is 100 millimeters of mercury. Pressure meaning what force it exerts on all sides of this container. Here there's fluid, so it's exerting pressure. It wants to go in all directions, and some of it is going to come and it's going to enter into this fluid. So, and then some are going to come back out, some are going to enter again. So if you start out at the initial state here, I'll come to my pen, and that initial state is 0, right? We have none of that gas, none of that oxygen dissolved. And now we go to the state of equilibrium after you've let it settle for a while and you know that it has a certain solubility, and some of that just from those molecules crashing into each other will come and become soluble here in this fluid. To what extent? Well, this will happen until the pressure exerted by that gas here in the air is equal to the pressure exerted by that gas in the fluid. So the pressure is equal in both of these. the pressure exerted by that gas. So it's 100 millimeters of mercury here and 100 in the fluid. But the most important thing to notice is that the number of molecules is not equal, correct? Here in little balls, we have 5 of them in the fluid and many more of them here in the gas portion, and that's at equilibrium. So equilibrium of these gases is going to be fewer molecules dissolved than it is in that contiguous area, which is air. Okay, very important concept. Now, solubilities differ. Carbon dioxide is 20 times more soluble in water than oxygen is. So the transport of that carbon dioxide is a lot easier than it is with oxygen. And we'll see how we get around that problem, right? It's definitely a problem. So oxygen, because it's not very soluble in water, it's going to be terrible to try and transport it just in the water portion of blood, which is in the plasma. So you're going to need some sort of molecule that helps it along. And that's what happens. Oxygen is going to attach onto hemoglobin because on its own, it's not very soluble in that liquid. Okay. Oh, that's my little diagram of oxygen not being very soluble in water. Keep it light here. Okay. Oxygen. You have a picture of oxygen there dissolving. At equilibrium, the partial pressure in the air and the water is equal. That low oxygen solubility means the concentrations are not equal. And now the only difference in this diagram is that I've given you the molarity here. So don't freak out on this. It's just to compare. That means how many molecules, particularly in the air here, is 5.2 millimoles per liter of that oxygen. And when I compare it down here, I only have 0.15 millimoles per liter of that oxygen. Okay, so concentrations are not the same because these molecules are not immersed in the same material. One is air and one is water. Okay, low solubility. Now we'll want to compare that. Look at the 5 little balls there that are able to dissolve, and that's all it will do. We want to be able to compare that to how it would look if you did the same with carbon dioxide and started out with 100 millimeters of mercury pressure in a container. And this is what it would look like. So you'd start out with this would end up, you don't start with 100, but you end up with 100 millimeters of mercury here, 100 millimeters of mercury of the pressure of the CO2 here, and still, even though it's much more soluble than oxygen, the number of molecules is still not equal. I have 5.2 millimoles per liter here and only 3 millimoles per liter in the fluid. Okay, I hope that's clear. These diagrams are in your text, so be sure to look at them there over and over again if this is a confusing point. Temperature. Okay, temperature, cooler liquids dissolve more gas molecules. And although blood temperature really doesn't change much, it is slightly lower close to the lung, which is interesting. It drops a tiny, tiny bit. But just think of it as not changing a whole lot. So that's not a variable that's going to be huge. The pressure gradient of that gas. Well, the higher the pressure means more gas molecules present. If you have just inhaled a lot of oxygen, you're at sea level and you've got a huge partial pressure of oxygen because you have 21% of that atmospheric pressure, which is sea level, then you're going to be able to move a lot of that oxygen out of the alveoli and into the liquid, which is the blood. If you're up on Everest, it's going to be a whole lot harder, right? So the pressure gradient of that gas, of where you are, is going to also matter. Another interesting example of gas that exerts partial pressure, and maybe some of you can relate to this, has to do with decompression sickness, the bends in divers. So individuals who dive, they're going to go down to great depths in the water. So let's say they're looking at the kelp forest. They're diving down and they're going deeper and deeper. what happens there is that nitrogen is now under greater pressure because you've gone down deep and you have all the pressure of that water pushing. And then that nitrogen is in the blood. And what will happen in decompression sickness is that nitrogen becomes more soluble under that condition of a higher pressure. So it becomes more soluble, and now you have more nitrogen dissolved in the blood just because you increased that pressure. So that's not a problem in itself, unless when you go to ascend, you do that too quickly. And if you do that too quickly, then that nitrogen is now under lower pressure and is going to quickly exit solution. And if it exits solution too quickly, it can bubble, it can form bubbles. Now you have bubbles forming in the blood, and it could block these tiny blood vessels. So the ascent is very slow, so that little by little that nitrogen that had dissolved into the blood under the higher pressure will slowly exit the blood again, and there is no problem. And then you can ascend up to the surface, and slowly those molecules will leave solution, right? You force them into solution by going down deep. So what happens in the bends, which is the name? The symptoms are pain. So you can have pain in the joints is one symptom. Itchy skin, blotchy skin, so they get little spots like this on the skin where some of those bit of sort of bleeding happens. Headache, confusion, and this can be terrible if you start getting confused underwater and you're not sure which is up and which is down or which way you're going. Is scary. Vertigo, and if very severe, unconsciousness. So I know that divers, I don't dive, but say they guide the bubbles that they're releasing from their tanks are ascending at a certain velocity, and to never ascend more quickly than the velocity of those bubbles. So we're going to stop there and continue part 3 in the next section. Thanks for listening, guys. See you soon.